talked about mass balance in flow reactor, and this is exactly the same. The principle underneath is the exactly same with the complete mixed flow system. And in other words, if we have a little piece of bread, sandwich bread, in here, and then we can assume something is coming in, something is going out, and by using those arrows, we can develop a differential equation like this. And then by using the principle of definition of differentiation, we can come up with this kind of solution. So I hope everyone now are familiar with those derivations. Okay. And I also ask you to do by on your own by practicing this example, and also I ask you to submit as homework. And I'm not going to go too much in detail about this equation, but I will come back in chapter 9. But as you see here, so far we had talked about arrows that is associated with the velocity, which is q, and also reaction. And in here, we can, as you see in here, and we have dispersion effect. And if we carry this on, and then we can have this kind of equation. So without this, and this is exactly the same as flow reactor, and now we have dispersion term. So if you go and check the classic chemical reaction engineering, this is the kind of representative equation, and actually this is the most important equation during entire this class, and so I want you to take a look at this, and eventually you have to know how to drive this equation and solve this equation later. Okay, and then I talked about the eutrophication or algal bloom, and at this time, as I said a few times before, we try to model the Han River algal bloom in the Han River. And what is algal bloom? And we often call this as eutrophication. Eutro means rich, and U means rich, and troph right here is food. So eutrophication is food-rich situation. And in here, food is a nutrient, and in our case, nitrogen and phosphorus, etc. Okay? So if you have too much nitrogen or phosphorus in your water, that means you have too much food for phytoplankton. And the phytoplankton will get fat, or they become too many. And then they become dominant species in whole water body. And this means they just have phytoplankton. No fish, no bird, well, bird is not living inside the water anyway. So, no competition. So that means it's not healthy water. Healthy water means there's some balance. You need to have somebody else that you can compete with. You need to have somebody you can just play with, something like that. And if you just you're going to be pretty lonely, and that is not healthy ecosystem. So, and this is the problem is unbalanced ecosystem because we have too much algae, right? because of that, fish cannot live in there happily. And also, if you draw the water, and you have to treat it very well because it has a lot of stuff inside, and they can make color and odor, and still have some dirty material that is not good for your health. And also, sometimes it's not really good to look at. Sometimes it's good because color sometimes beautiful. That's just kidding. All right. So, what is nutrient? Why do we need nutrient? We need this kind of thing for our growth, right? And we need carbon, hydrogen, and oxygen, nitrogen, phosphorus, and other elements for our health. Because those are necessary to move all parts of my body. And that's the same story for phytoplankton as well. And because to help it grow, we need warm temperature, we need enough light energy. They like this calm environment, not very rapid and turbulent. And sometimes this and that may be almost the same. Also, as the living entity, we need something to eat, right? So those food includes this kind of material. And if you have anything that is not enough for you, then that it can be a problem for you. Let's say if you need vitamin C, if you don't have enough, you have a problem. If you don't have enough vitamin D, you have some problem, other problem. And it's the same story for nitrogen and phosphorus. If you do not have enough nitrogen, you cannot produce enough protein, right? Because nitrogen is the source of protein, right? And phosphorus is the source of ATP and ADP. And ATP, ADP, that's very important for your energy exchange. So if you do not have enough nitrogen, and you have problem of producing protein in your body, and same story for carbon, but carbon is already too much, so we don't really care about that. But phosphorus, nitrogen, that has not been enough so far, but because of our activity, they become much more in our surface water. For example, we feed a pig and cow for our food source, and to feed them, we just give them a lot of how do I say, their food, but they make a lot of byproducts. And if we don't treat them well, and eventually those will flow into our water body. And because we do that in a very large scale, and now the amount of pollutant entering because of that is much more than before, right? So those can deliver a lot of more nitrogen than before, a lot of more phosphorus than before. So that's us, the humankind, made a lot of problems. So we need to fix that. And so when we talk about something that is not enough for you to grow, we often say, borrow the idea of living. I don't know exactly first pronunciation of this. It's German. Living. So low meaning. So that means if you need something, that only element will interfere you. That only element will drag your leg to not to grow enough. Okay. In this case, we have so many different phytoplanktons. We are talking about now the growth of phytoplankton, But among phytoplankton, we have good phytoplanktons and bad phytoplankton. Good means the good phytoplankton means the zooplankton they like it. So they can be a part of the food chain. But bad phytoplankton, and they have toxicity. The zooplankton cannot eat it. So the cyanobacteria or blue and algae are kind of bad ones. So zooplankton do not like it. So they can just grow without any competition in bad situations. And because it says it carries the name of bacteria, and bacteria is is located at the lower grade of food chain. That means cyanobacteria is between bacteria and phytoplankton. Okay, so that means it's very low grade, not animal, but the biological stuff, and then they have good ability to survive in any situation. So this one explains if you have a water jar and if that is full, then you have your water level is going to be like that. But if you have one piece of your side that is like that, and then your water level will be controlled by this level, right? So that's what this Lewis law minimum says. Okay? And the minimum food, minimum element will limit your growth, will control your growth. That's the rule. So in this case, if phytoplankton is small, then we need that. We apply that principle to control algae, because if we eliminate phosphorus, then we can just make them grow less, right? So, as I said, eutrophication is food-rich situation, and we said oligo, meso, vitro, hyper. Okay, and hyper often we use that. Hyper is too much, right? And oligo is too less, and meso is something between, and this is somewhat rich. And this is not a definite category, and sometimes the concentration lower than that can cause eutrophication, even though if phosphorus is about 10 micrograms per liter or less, and still you can have eutrophication. But in general, the scientists somehow searched the paper and they came up with this kind of suggested value. It's not fixed value, right? Sometimes says eutrophication, the standard is about 20. But the eutrophication originally was the natural phenomenon. In other words, if you have fallen leaves in autumn, and if you have dead animal, and if you have water, and if they just somehow buried together, it is going to become wetland or swamp. Okay, and then if long time it goes by, then that land is become a pure land. So it's like the life of the water, and it's not always like that. So they become part of the land, and then the waterway became another. We need to find another path to flow through. So eventually, the eutrophication or the forming of wetland was part of the natural process. But today, we produce nitrogen and phosphorus too much in a very local area, and then so we make it faster to happen. That's the problem. So natural may be okay, but artificial or human induced is not okay. So if we made mistake, we need to fix that. And Vollenweider, as far as I know, he lived in Switzerland, and he worked in United Nations, and he was in charge of analyzing the lakes in the world, and then he came up with a very nice idea. And he is a limnologist, I guess, and I heard he is living in Canada. I don't know why do I need that. And anyway, and he says it has a lake, and we have a phosphorus. And so and in here we can develop things like that, and then we have a VSAP is the process of settling in here. So if we let's say we have just one cube. By the way, where's my home? Well, forget it. We can set up mass balance equation like this. Okay? So in here we have studied about this mass balance of C and F reactor. Okay? And so we are going to talk about it later. So lake is one big, completely mixed reactor, and then we have we know the loading rate, which is right here. You can say as W. Q times P0 is something coming in, and we say it's a loading rate. And the reaction rate is in here, and we can also have if you know the reaction rate, and we can say it like that, but many times phosphorus, they get absorbed on the particle, and then we assume they settle together with those acids, and then so it is more common that we express the reaction rate of phosphorus in water in the form of settling rate. Okay, but this and that. Both this term are just mass per time due to reaction, mass per time due to settling. But this time we talked about their meaning about the relationship between the velocity and decay rate k. Right? Steady state means we will make our life simpler, right? All right, so I have this one, and then we'll just play with this equation. And since this one is 0, we can solve this for P, right? So we just move our P over here, and then we can move these two terms to denominator, and then we can come up with this answer. Simple, right? So we solved the situation. That's it. And then we want to use this equation to get some more information. And we talked about phosphorus level, which is 10 micro, 30, well now let's say just 2. And I want to know what kind of W will make phosphorus, because P is now the function of W, right? So we know Q, we know A, we know V, and if those are, let's say, fixed or constant, then P is going to be directly proportional to W, right? So if we have more W, then we have more P, right? Less P, less W, less P. Okay? So we'll play with this equation a little bit more. We'll just divide everything by 3, because I know H H times A is V, we can have this kind of equation, right? Okay? And then we know V divided by V is the inverse of hydraulic detention time. We talked about that. Hydraulic detention time. Yeah. So this is inverse of it. And then we still, we can just multiply everything by H. Then we have this form. And then we can say the loading rate per area of the lake is W prime. So this and that, those are exactly the same, and we just change the form of equation for our own interest. Okay, from here, let's say I know my settling velocity is 10 meters per year. In 1 year, it set us 10 meters. Very, very slow. It's like colloidal motion. And then I can have 10 right here. So then I can rearrange my equation like this, right? Because I can just move this whole thing to here. So I have it here. So eventually what I'm going to have is, let's say, I'm going to draw a figure between HR and W prime. And then I will have something like this. And what this will be, this is going to be 10 times P. And this slope will be P. Right? But I have something different. But we should change this to microcalculator, not millicalculator. This is too much. Microcalculator. So actually, this figure and this figure is, those are exactly the same, right? And in here, what you see is logarithmic scale, right? And what you see in here is logarithmic scale. If you change it to logarithmic scale, then your equation is going to be a little bit different. It's like a little bit curved, right? Okay. So, and what did I say? I said 10 and 30. If you want to have 10, then you can insert 10 in here. If you want 30, then you can insert maybe 10 times 30, and this is P is 30, right? So you have two different lines in this case. But because I changed this to logarithm, it's a matter of click in your Excel. If you click here and change it to logarithm scale, you can just have it right away. Okay? So I will come to here because those two are the same curve. So I have 10, P equals 10 here. And under this curve, I will have concentration of phosphorus less than 10 microgram. Right? And in here, if I have 30, from here up, I will have phosphorus concentration higher than 30 microgram per liter. If you want to 20, then you can have it, right? So, and this is the, if 30 is the standard for between utero and meso, and then I can say, in here is the eutrophication area. And less than 10, I have an oligotrophic area. Okay? And then my problem is if I have this much coming in, and my depth is this. R is, by the way, the inverse of your hydraulic retention time. So you already know H and R. Okay? So if you know your depth and your retention time, then let's say this is your place. I want to make my lake Mr. Traffic or illegal traffic. Then you have two options. You can move this dot to here, or you can move this dot to there. Which is easier? It's your choice. Okay? To make this one this way, I may have to increase my age, which is depth. So I have to dig my leg. Maybe in here 10 times or 100 times. Is that possible? It's going to be a little bit difficult. And also, I want my detention time very short, so that I can make my R very big. Very short means big flow rate and small volume. But you need to keep providing water. Is that possible? That's going to be another. That is going to be difficult as well. So, but in here, if you want to make your dot this way, I want reduce my W divided by A to this much. Reduce W. What is this? Reduce W. Reduce W. Right here, this one. I want to reduce my loading rate. I think that sounds more reasonable, right? So then, but it is very difficult for us to remove my loading entirely. So this one suggests us how much should I remove to make this leg a legal job. Okay, then, okay, from here to there, okay, then, okay, this is how much. The difference of those two is how much that I need to treat. So then, we can say, okay, P0, now it's 1 million per liter, you need to have it at least 50 or something like that. Okay? 40, depending on your calculation. So this is very simple analysis, but this one tells us a lot of concept behind the analysis of leg situation and use of this equation to explain it. This may look simple, but this is very important. I'm not talking about just settling velocity, just hydraulic detention time, etc. I want to make kind of a big picture like this, and then think about what's coming in, what's going out, what is happening inside. And then I need to think about why this one happens. Why this happens? And what can we do, right? Then can we do something about Q? Maybe not. Can you do something about H? Maybe not. Can you do something about sunlight? Maybe not. Can you do something about temperature? Maybe not. Can you do something about incoming phosphorus concentration? Maybe. Right? That's very important. Maybe. Then how much? How much? And if you are environment activist, you will say 0, nothing, or kill me, something like that. But that's not what engineers are doing. Okay? We need to tell them this much, this place, this time, right? So we need to have a very practical, provide practical solutions. So this is just one example of using this kind of equation. As I said, we can use this one. This is a lot simpler. But if you want to have a leg in the world, from Korea to Africa, you have a small lake, big lake, dirty lake, clear lake. So you will have all kinds of different values. In this case, we now understand why Dr. Vollenweider had to use logarithm scale. Because while this one is a lot clearer and straightforward, this is a lot easier to understand, and this one is a lot better to include every lake in the world because it has this kind of scale. But this is already 1,000 times there and just 1,000 times there. So logarithm scale, he used it not to confuse you, to include every leg in the world in one figure. And that's another very important intuitive idea. Okay? So I want you to, and this is again just one of the examples of doing so. Now we are trying to explain what is happening in algal blooms in the Han River. And probably in 2 weeks, we need to report the whole situation, and then a lot of mass media, including the newspaper and the TV, they will come and then they will listen to us. We need to have very nice answer, but the Han River is big system, very complicated. And then if I tell them, this is very complicated and very difficult to explain, then that is not the answer they want here. They want, what is this? What is that? So what? And then I need to say, okay, this is this is that. Period. That's what they need. But we engineers and scientists need to somehow simplify the situation and explain to the people so that they can make decisions. And then they were, okay, then they will think, okay, we need to do something about that. At least they said we need to pay for something about that. So that's very important. All right. So we talked about that, and I will just do it over, but I will just do it boldly. And hydrogen radiation sign, that's a mass of water inside your system, and flow rate is a Q. And we, to calculate the mass, we all know we have to multiply by density of water, but density of water here and there are the same, so we can cancel those two. So that's why we have V divided by Q. That must come from mass balance of water, right? And in here, we just assume the water inside the lake, water leaving the lake, they have the same density. That cannot be true sometimes, okay? If you have different temperature, you have different density. If you have different water concentration, you have different density. But very small, not very small scale. But if you don't need, I don't think you need that in your everyday life. So this is okay. And then for the treatment plant, you have activated fluid system, and then you want to calculate the residence time of your cell or your pollutant. Okay. In this case, we have the same principle. Well, how much pollutants are in your system, which is V times C, and how much are leaving. In this case, I should write this as minus and minus. Oh, this is and if you write a mass balance, you have something going out, something reaction, and something settling. Then those three are something going out, right? Because those are minus terms in your mass balance equation. So you need to have that, right? Think about this. And these two are something going out, right? Right? So if you had K, P, V, then this whole thing is something going out, right? So then we need to have unit of time. So in here, if you mass, and this must be mass per time, so that we can have in your denominator, if you have mass per time, then if you split it over, then you will have a unit of time. So your cell rising time definition is this, and if you go back to your biological wastewater treatment plant, then now you will have less problem, right? So if you have activated sludge system, and then if you return your sludge and waste your sludge, then somehow you find if your system has this kind of stuff, then you can use that. So you have to just keep concentrate on what kind of system are you talking about. And are you talking about just this only, or are you talking about just this whole thing, right? So it depends on your system. Then what you need to think is the error that eventually get out from your system. Okay. Then if you add everything in there, then you will be fine. So I'm not going to talk about this too much in detail because those are in your another textbook. So I just give you an idea and how you can use our mass balance equation in your other class. Okay, this is x is factorial in your activated slot system. So we have the same VDCPT, right? And then something coming in, and something going out, and something going out as return sludge. And then this is growth factor. Bacteria can grow. And S is what? S is BOD. And they eat food. And in our case, we regard S, which is BOD, as the food. Okay? And this is K, decay, or they die because they are biological entity and they grow old and then they die. Sometimes they can get eaten by other superior level organisms. So if you have steady state, then you have 0, and then you can just play with that. But problem is S is not constant, and to solve this one, you need the constant, the equation for S as well. But I'm not going to talk about that. Anyway, in here we have this the new my growth rate can be this, and then your K can be this, and then you have a different definition or term, and then you can play with those. So once you know the general idea about the system, it is relatively easier to understand the other system. And then if you kind of keep flow in your brain, then you can just simply or play with those puzzles and to match, and that way you can make a big picture. So solid detention time, the definition is this, and again this is how much are there and how much are going out, and then people are playing with that. In your aeration tank, if you have a BOD, DSPT, then you have something coming in, something going out, and then something gets eaten, right? And so you have this kind of stuff. So this whole process are going to be the major idea in your biological wastewater treatment plant, but the basic principle of mass balance is exactly the same with ours, right? So once you know what is going on in our lake, and you can understand what is going on in your river, and also sea, ocean, whatever, and then also if you just flip it over, you can apply this idea to any kind of reactor. Any kind of reactor means including water treatment, and wastewater treatment, and rainwater treatment, whatever, okay? And only thing that we have to study is, what is this? We don't know. It can be a K, C, the power of first, because we need to know reaction rate. And sometimes they can have this kind of form, and sometimes the growth rate, as you have in here, we had a little different form. It's okay, it's okay. And people, scientists or engineers and our seniors, they already studied about that, and that they would suggest for, even though those are not perfect anyway. So if we know that kind of stuff, then we can later provide that information to here. That can be reaction, or that can be acetylene, and that can be something somebody else coming and taking, and then anything, right? And so even though you don't know at this time, but in here we know what is RSU. RSU is somewhere there, right? Okay. So That's I just want to share our application is not different from application in other class. So congratulations, right? It's very easy, and I will just give you a little taste about the lecture 4. And lecture 4 is relatively very easy, and these are all kinds of loadings. Loading can be right here, okay? Loading can be if you have just a fuel tank or some big truck. If the big truck is somehow, it's a bad example, but somehow they jumped into the lake, like here. One day just jumped in, and then you start to have problem, okay? And that's the first situation. Step loading, step is now stairways like this one, okay? Step. Step is what? One day you start to have a wastewater treatment plant. They start to operate, right? Start discharge wastewater. Then you have problem from day one. You have problem all the way, and then we have some big area, and there are a lot of industries, and then some factories they get built more and more, and then they have depress more and more problems. Then you can have a linear, or you can have any kind of function if you know, right? And then so that's linear loading. Exponential loading is they follow exponential function. Sinusoidal, that's a sine curve. If you have coastal area, if you have a irreversible, ebb tide and flow tide, right? And then you have this much, that much, this much, that much. And if you have a combination of those, you can just add them together, so you can have total solution, right? Okay. So in here, I have one big tool to deal with this situation, which is integrated factor method. I will just do it very quickly, and then want you to practice. Let's see, dc dt is PC, PT times C times QT. It's just like this. V dc dt equals W minus QC minus KC V. Right? And then we can rearrange this equation like this. This one. Divide everything by V, right? And then we can dc dt, and by lambda in here maybe Q divided by V and K divided by V. No, just K. Right? And by the V prime is, so this one and this one exactly the same. Okay? Actually this one is easier. And let's define my integrating factor is e to the power of like this. PT in here is like here. Okay? And we'll multiply these two both sides. So we'll have here, here, here. Okay? Very good. Now, let's differentiate this one. If you have this kind of equation, if you differentiate, you will leave this one here and you will differentiate this one, and then you will leave this one, differentiate this one. So if you differentiate uv, then uv prime and u prime v is what you get. Right? So this is reversed way. If you have things like that, then you can simplify like this. So we have the same term in right hand side, but we simplified the left hand side. So, and then we can integrate both terms. Right? If you take a look at this one, if you integrate, if you have this one, if you have difference equation, if you have integrate, and it's like you already have differentiated, and then you integrate. Differentiated, integrate, and then you will have the same form. In other words, this thing right here is the solution. Because just you did it. You did it, and it was here, and you flip it, and then get it back. Differentiated integration. So you have the same stuff. But you have a kind of interval, right? From somewhere. And in here, we still don't know. We still don't know. Right? But if you can somehow integrate this one, you can have C without a problem. Okay? So, another homework. Let's say you have this one. I want you to solve your C using this principle and just add it to your homework and then give it to us. Next week, I guess, after I am done with the particular solution, I think we'll have midterm exam.